Hello guys. So for this second example, uh, the question is draw the shear and moment diagrams for the beam shown in figure, and then the support at B settles 0.04 meter. And then take your modulus of elasticity E equals to 20 megapascal, or which is equal to 20 meganewton per meter square. Then your moment of inertia is 4 times 10 to the power of negative 5 meter to the power of 4. So as you can see here, this example is a bit different. As you can see, there is a settlement or deflection, displacement at B. There's a displacement at B, which is 0.04. As you can see here, this is your B. So the force here cause deformation displacement of 0.04 here at point B. So this will become your resultant displacement when you are developing your when you are writing your compatibility equation. So as you can see, the distance, the span of the beam is 16 meter. You have load acting on the first segment of the beam, A to the B. In the middle is 130 Newton. And then what you need to do first is to draw. First thing is to draw the primary structure and then the redundant force structure. Where in this example, in this solution, we remove the redundant support at B, the roller at B. We remove the B, and then the roller is being replaced with the force. So as you can see here, the actual beam is here. Then your primary structure is here, where you retain the actual force here, 130 Newton, acting at 4 meter from A. Then there's a deflection of delta B due to this force. And then you have another structure, which is we want to measure the deflection at B also, but this deflection displacement is due to the force acting to the force of by, which is replacing the roller support. As you can see here, both displacement is considered downwards, and then the value of downward will be considered as positive, but the directions and the positive related to the direction is up to us, but need to be consistent. So in this example, we use downward positive. So we assume that 0.04 is resultant displacement due to this force 130 Newton and delta B, and then plus delta BB, delta prime BB, which is due to the BY. So based on your structure, your previous structure here, so your equation for finding your displacement based on the formula which will be given in the exam, the first primary structure will be used this setup of load and support here, where there is a variation of A and B, which define the position of your load. So in this example, as you can see, A and X need to be within A. So that it's a bit tricky here. As you can see here, your load is here, but your X is the distance from the support from the end to the point of interest, which is we want to know the displacement at B here. So the distance X is not from A but actually from C, which is 8 lah, your distance x, because your A is from C to load 130 Newton. Yeah? So this is your A, this is your B, so this is your X lah, this is your A. So this becomes your B. Okay, can you follow? This is your B. B is from support towards me, but one thing is B is not A. A plus B is equal to L. So X must be within, as you can see in the formula, X must be within 0 to A. So that's why your X is here, so your A is here. Then only you become, it's a flip lah. As you can see, it's a flip. You need to flip this formula. So basically you will use this formula. Worth noting here, as you can see, there is a negative here, because in this book, it takes negative as a downward is as negative displacement. Downward is negative displacement. As you can see also here, negative displacement. Downward is taken as negative displacement. And also, so that's for the first structure here lah, primary structure, and then for your redundant force, structure with redundant force, you will use this equation, PL power 3 divided by 48 EI, and the X point of interest will be at middle. So guys, just to explain a little bit about this table, which is found in the textbook of Hibler or structure analysis. As you can see, the first column on the left is your setup of load and support. So you need to choose which type of load and supports that define your problems. And then the second the second column is the maximum deflection. So basically, as you can see, maximum deflection depends on the position, the point of interest given usually here. Usually at the end of the formula, as you can see in the second setup here, where the maximum deflection Vmax occurred at x equal to L over 2. So the position is at L over 2. If you want to know the displacement on not on the maximum point, but on the point of interest that you want, so you can use this equation between 0 to x, between 0 to L over 2 x. So you can find that L over 3, L over 4, and so on. Same goes over here. So your point of interest will be displacement based on the value x you put in here. So you get the displacement at the point of interest. It is important that the point of interest is important because when we resolve, for example, in this example, we want to find the support, the force, the reaction at the support. So the point of interest is important because if you have redundant here, so this will become your point of interest. But if your redundant is here, C, for example, then you want to know the deflection at C. For example, and so on. So the point of interest is important. But in this case, for the second redundant load applied, the point of interest is the same as the maximum deflection, which is at L over 2. So this equation will be used. But then again, the negative is not taken because we take, as you can see here, we take positive downward, we take as positive. So 0.04 downward, positive delta B downward is positive By times FBB, which is delta prime BB, which is also downward, is taken as positive. So this is your compatibility equation. Compatibility equation 0.04 equal to delta B plus, which is this is delta prime BB, also equal to By times FBB, which is FBB is the coefficient, how much force By causing deflection of delta prime BB. So By times FBB is equal to delta prime BB. So the first one, so this is your equation here. We use PBX over 6 LEI, L squared minus B squared minus X squared. So this is your equation. You put in your value. So 130 is your P value, B is 4, X is 8, and so on. And this is your E and I. So you get, this is your value of delta B, displacement at B due to force P. And then you calculate the FBB, which is using the equation here, PL power of 3, radian for 48 times EI. So key in your L and P is equal to 1 lah. Because we want to know the magnitude lah, the coefficient. So the P is actually should be By, but for FBB is like the coefficient, how much, it's like perkali, multiplier. So basically this coefficient translate By into delta prime BB. So we put one magnitude, which is actually just one value, and then this is actually unitless. So L is 16, and then your E, your I, this is equation. So your value of FBB is 1.39 times 10 to the power of negative 3. So you have both value of delta, this displacement. So you substitute into your equation, which is all positive, acting downwards. So solve for By, so you get By negative. As you can see, By is negative because which shows that By is in the opposite direction of the one that we assume, downward. So actually By is acting upwards. So I think it is important for you to remember, for you to be consistent with your direction, because it reflects, it defines the direction of force acting on a structure. Because you might get this wrong, then when you solve this wrong, then you also get wrong on the other reaction support. So based on that value, so based on this value, we got there, and now we want to try to find AY and CY. So using moment equation at C, AY, we take counterclockwise positive, so AY times 16, we assume AY upwards. So AY is clockwise, so negative, times the moment arm 16, which is the full length, and then 130 of force times 12, the moment arm towards C, and then the By times moment arm of 8. So you get AY is equal to 53 Newton, as you can see, positive. So our assumption AY acting upwards is correct. And then you solve for FY positive upwards. So FY, AY is 53, BY is 89, CY minus 130, because force acting downwards. Then you get your CY is equal to negative 12, so negative, which is downwards. So this is your final internal forces, final reaction forces acting on the structure. So based on this, you can draw your shear force diagram here. Shear force diagram. So this is 53, and then there's no force acting, so flat. Shear force remain 53, and then at this point where the load applied, so 53 minus 130, so you get negative 77. And then there's no force acting, and then a reaction force at By upwards 89, so 77 negative 77 plus 89, so you get 12. Then 12 here, so it's balanced. So shear force is balanced, and then based on the shear force, you draw your bending moment diagram. So as we said earlier, square, rectangle, so rectangle shear force diagram will translate into triangle bending moment diagram, and triangle shear force diagram will translate into a curve bending moment diagram. So as you can see here, the moment is increasing due to force of AY. Then the moment change direction, reducing towards negative direction uh, due to force 130 Newton. Hits 96, and then increase again due to reaction at B9, By. So up until C, there is no moment. So it is important to remember. It is important to remember that when you are trying to draw your bending moment diagram, you need to remember that there's no moment at pin support, pin roller support, but there is a moment at fixed support. So if there is a moment at fixed, that if you are fixed support here, for example, then there will be a moment here. It will start with the moment, or it will end in the moment if you have fixed support here. So I hope you find this comprehensive. Do contact me if you have any inquiry. Thank you.